When a transient short circuit occurs on a high-voltage transmission line, standard protection relays clear the fault in fractions of a second. The grid is engineered to absorb this without interrupting service. Yet, in regions packed with data centers, these minor, distant voltage dips are triggering catastrophic load losses. In July 2024, a localized voltage fluctuation in Northern Virginia caused 1,500 megawatts of power demand to vanish from the grid. 2 months prior in Ireland, a remote fault wiped out 387 megawatts of load instantly. At that exact moment, that represented 52% of the nation's entire data center demand. Grid operators classify this precise chain of events as customer-initiated load reduction, or CILR. These hyperscale facilities are disconnecting their loads in milliseconds, bypassing human intervention entirely. The sequence unfolds before an engineer can even register the event on a control room display. The bulk power system is not experiencing a failure of generators or transmission lines. It is facing a behavioral failure, driven by massive, interconnected computational loads reacting simultaneously to a single stimulus. When gigawatts of load drop off the grid instantly, the physics of the system aggressively shift. The mechanical power injected by generators now vastly exceeds the electrical power consumed by the remaining load. Because that excess energy has nowhere else to go, it converts into kinetic energy, violently accelerating the steel rotors of the turbines. This sudden supply-demand imbalance forces a sharp, rapid upward spike in system frequency. If that frequency climbs high enough and hits a critical upper threshold, generator over-frequency protection relays will automatically trip to prevent the turbines from physically tearing themselves apart. At this point, the grid has violently lost its foundational load, and now it has lost its synchronous generation. The system chases a cascading blackout. The strict logic built into data center hardware to protect server racks is directly threatening the survival of the larger electrical network. To understand why this happens, we have to examine the hardware sitting between the utility grid and the server floor, the Double Conversion Uninterruptible Power Supply, or UPS. This chart shows a standard ITIC curve. It defines the strict voltage tolerance envelopes programmed into UPS firmware to protect highly sensitive information technology equipment. During a minor transmission fault, a brief voltage dip easily falls just outside this acceptable safe zone. Looking at the internal topology of the UPS operating in standard double conversion mode, the reaction to that minor dip is immediate. The static switch opens, completely severing the active server load from the AC utility grid. The entire facility transfers its demand to internal battery backup to ride out what it perceives as a severe disturbance. The outcome is entirely asymmetric. The GPUs continue processing data without dropping a single cycle, but the local grid absorbs a violent, step-change load rejection. The UPS is not malfunctioning, it is executing its protection logic flawlessly. That rigid design philosophy is the core systemic threat. Traditional composite load models used in grid planning view demand as a blend of passive motors and generic electronics. They are mathematically blind to CILR and fail to predict these simultaneous drop-offs. Because of this, the North American Electric Reliability Corporation now mandates a new regulatory framework, the PERC-1, or Power Electronic Reconnecting and Ceasing Model. Instead of treating a data center as a static sink, PERC-1 explicitly models the precise low-voltage trip thresholds and duration curves that cause load shedding. It also maps out the recovery fees, incorporating the time delays and dynamic active power ramp rates that occur when the facility attempts to reconnect to the grid. Crucially, regulators require these parameters to be field-validated from actual hardware installations, rejecting default manufacturer estimates. Without this high-fidelity modeling of voltage-sensitive trip behaviors, grid operators cannot perform valid dynamic interconnection studies or calculate the safe operating limits of their networks. That addresses how facilities react to grid faults. But large-scale computational loads pose a second, entirely distinct threat during normal fault-free operations. This graph maps active power over time, showing that training a massive AI model is not a steady draw of electricity. It is a highly active, synchronized process. During the synchronization phase, data transfers between nodes. Information technology equipment energy consumption drops to an extremely low baseline. Then the forward propagation pass begins. Hundreds of thousands of GPUs ramp up to their maximum utilization capacity simultaneously. This is immediately followed by the backward pass, where parameter adjustments finish and the load drops abruptly back down. When clustered at scale, this coordinated processing generates massive power swings, driving demand up or down by 10 megawatts in a single millisecond. AI data centers are no longer passive consumers. Their synchronized batch computing injects violent, high-frequency active power demand cycles directly into the local grid. When those aggressive demand cycles form a rhythmic, repeating pattern, they introduce dangerous physical stresses to the bulk power system. These graphs show real-world measurements of these demand rhythms echoing across the transmission system. We can clearly observe that these active power oscillations fall directly into the dangerous 10 to 50 Hz electromechanical range. This triggers a phenomenon known as Subsynchronous Torsional Interaction, or SSTI, where the power electronic switching of the data center locks in with the natural resonant frequency of the grid. The energy from that resonance does not disappear. It is physically absorbed by the heavy hardware of nearby synchronous generation plants. The electrical oscillations convert directly into mechanical torque. This rhythmically twists the generator shaft back and forth, severely increasing the risk of fatigue-induced structural failure. The act of executing parallel AI software code is now fully capable of physically fracturing heavy industrial generation assets miles away. To stabilize the system, transmission system operators are mandating a specific hardware engineering solution for massive data centers, fault ride-through, or FRT, compliance. This requires moving away from the traditional isolation approach toward grid-friendly topologies. Under FRT logic, when the grid experiences a severe voltage sag, the UPS maintains the AC utility connection. Instead of severing the load entirely, the UPS discharges its internal batteries directly into the DC link, buffering the sever racks from the external drop. Simultaneously, the grid-side rectifier stays active, precisely managing both active and reactive current injection to help the external utility network recover. By utilizing internal battery storage as a dynamic shock absorber rather than an emergency escape pod, hyperscale facilities can absorb transient grid events without triggering a CILR crisis. This engineering approach is backed by rigorous operational compliance. Facilities must now install continuous dynamic fault recording equipment and maintain direct SCADA-based telemetry links with balancing authorities. Commissioning these sites mandates exhaustive physical validation. Planners require full load and no load tests on the as-built infrastructure. Testing with standard resistive dummy loads is no longer adequate because passive resistors fail to replicate the complex, nonlinear switching behaviors of actual server power supplies. Engineers rely on megawatt-scale power hardware-in-the-loop laboratory testing to validate how the exact facility models interact with grid dynamics before a single server goes live. Deploying gigawatt-scale computing requires absolute harmony between mathematical planning models, utility operators, and physical data center hardware. Data centers have grown too large to be treated as passive network participants. To sustain the AI boom, these facilities must be engineered as active, stabilizing components of the bulk power system.